Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Fawad, Assistant Professor at the Department of Physics Cust. I am here with online lecture number 1 of the course Luminescence in Materials. The course code for this course is PH671. Today's topic is spectroscopic terms. So let's start it. The outline of today's lecture is electronic configuration. We will talk about little bit about fundamentals of electronic configuration. Then we will explain and discuss spectroscopic terms, and at the end I will solve few examples how to derive spectral terms for different atoms. Electronic configuration, we have already done it before, but let me summarize it once again. That we are all this electronic configuration tell us about the arrangement of electrons inside sub-energy levels of an atom. So these are different electronic configurations. You can see 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6, 3d10. So this is for K shell. It has got 2 electrons. So for this, the electronic configuration is 1 is 2. This 2 is 2, 2p6 is for L shell, which has got 8 electrons. So 2 are in s orbital and p are in 6 are in p subshell, and then for M shell. But this n square configuration cannot physically distinguish between the electrons. So according to Pauli exclusion principle, we must use sets of quantum numbers to decide if the sub-energy levels are the same or different. So here we go with the term symbols. The general form is written here. And what are these values of S, L and J? They are explained here. S stands for total spin angular momentum quantum number. So the 2s plus 1 gives us the multiplicity, that is the singlet, doublet or triplet state of the electron. Then we have L, capital L, that is the total orbital momentum quantum number, and then J, that is the total angular momentum quantum number. The spectroscopic terms symbols can be derived in this way, that is for if we are able to find S and then L and then J, so we can easily find the term symbol 2s1Lj for any electronic state. So let us first discuss S. For single electron, S, the spin quantum number would be half. For 2 electrons, that would be like 1 over 2 up and 1 over 2 down, but it depends on the cases. Sometimes both are in upper level, sometimes they are parallel, sometimes they are anti-parallel. Then for orbital quantum number, we have SPDF. So these SPDF orbitals corresponds to L is equal to 0, 1, 2, 3 respectively. Then for total angular momentum quantum number J, the J values varies according to Russell-Saunders coupling, which is called Ellis coupling. Here the J values vary from L minus S to L plus S. So for term L, which is given here, this L can be defined here as that if we have L is equal to 0, that will correspond to S. If L is equal to 1, that will correspond to term P, and then 2, 3, 4, D and F respectively. So let us calculate the term symbol for hydrogen atom. In order to find the term symbol for hydrogen atom, we already know that it has got only one electron. So first of all, we have to find its electronic configuration, that is 1s1. Now, for 1s1, we have s orbital. The single electron in the hydrogen atom is lying in s orbital, so that corresponds to L is equal to 0. Then it has got single electron, so the spin quantum number would be half. And then for total angular momentum quantum number, that would be 1 by 2. But how we have got this J is equal to 1 by 2? It's explained here in this calculation, that the J value in the previous slide was given with this formula, L minus S to L plus S. So if we put this L is equal to 0 and S is equal to 1 by 2 here, so it gives us 0 minus 1 by 2 to 0 plus 1 by 2, and that gives us 1 by 2 to 1 by 2. It means in both cases, L minus S and L plus S, we are getting the same value, that is 1 by 2 and 1 by 2. So it means we have got J is equal to 1 by 2. And then we already know that L is equal to 0, so the total, and it has got only one electron, so capital L would be equal to small l, and that is 0. And that 0 corresponds to S, so that S will come here. So that's why the spectroscopic term symbol 2s plus 1 Lj for hydrogen would be like 2s1 by 2. Now let us calculate boron 5 atom. Similarly, we will first of all find the electronic configuration, that is for 5 electrons inside the boron atom, that is like 1s2, 2s2, 2p1. So the last electron 2p1, that would we will try to find the spectral term for 2p1 state. So as it is in the p orbital, so p orbital stands for L is equal to 1 orbital quantum number, and as it has got one electron as well, so S is equal to 1 by 2. And then in order to find the value of J, that will vary from L minus S to L plus S. So if we put the values of L is equal to 1 and S is equal to 1 over 2 here, we will get 1 minus 1 over 2 to 1 plus 1 by 2, and we will get two values here, that is 1 over 2 and 3 over 2. At the end, as we already know that it is in p orbital, and that is L is equal to 1, and that L is equal to 1 corresponds to p term, so that p term will come here. Now this spectral term 2s plus 1 Lj for boron atom will become like this. Since the p is same, 2s plus 1 degeneracy is same, but we have got two values of J, so here we will get two spectral terms for boron atom. Let us now calculate the spectral terms for the ground level and for the excited level of sodium 11. Electronic configuration for sodium is 1s2, 2s2, 2p6, 3s1. So the ground state electronic configuration for sodium is this. Then for spectral notation for ground state will be like this. L is equal to 0, that is corresponding to S state. Then it has got one electron, so S is equal to 1 by 2. Then total angular momentum J is equal to 1 over 2. So it gives us the value of 1 over 2 from L minus S to L plus S. And as it is s orbital, and s orbital corresponds to L is equal to 0, and L is equal to 0 corresponds to term capital S. So the spectral term 2s plus 1 Lj for sodium ground state would be like 2s1/2. Now let's calculate it for excited state. We already know that when electron from ground state of S is excited, it will go to the p state, went to the p state, and for p state L is equal to 1 orbital quantum number. Then the total spin quantum number for single electron of the excited state of sodium is S is equal to 1/2. And then let's calculate the total angular momentum quantum number. That value varies from L minus S to L plus S. So if we put the values L is equal to 1 and S is equal to 1/2 here, we will get 1/2 to 3/2. So again we are getting two values for J. We already know that L is equal to 0, L is equal to 1, and L is equal to 1 corresponds to capital P term. So we have got again two terms for excited state of sodium. These are 2p1/2 and 2p3/2. So similarly we can find spectroscopic terms for other atoms as well. So that's enough for today's lecture. Thank you.